The particle and cell method is fairly simple. You have Maxwell's equations, and you have a Cartesian three-dimensional grid where there are electric and magnetic fields defined on that. And then you have particles, and the particles are ion and electron species. And the algorithm, we actually start kind of over here with interpolating the field effects, but logically, when a particle moves through the domain, it's charged, and so it deposits a current. And the motion of the particle itself is affected by the electric and magnetic fields that act upon it. So once we advance the particle, we accumulate the currents that it's deposited, and those then update the field equations that are on this Cartesian grid. Then we update the fields and interpolate the field's effect. So the algorithm just kind of bounces back and forth between this particle advance and a field update. So here's a little bit more detailed example. If I start out with a particle there, it doesn't look like my slide is not showing up the way it does on my laptop. But if I have a particle here, then I interpolate the fields to it that comes up with a new direction for the particle to go, and I advance the velocity of the particle. Then I project it some distance that just is kind of a spatial increment. And then once I've done that, I have to go through each actual cell that it passes through and then accumulate currents for that cell and update the position and the current density for that. So this, then I have a final state. And we did some careful analysis when we were doing this, so we have a really accurate count of how many actual data bytes it reads and how many floating point operations are done. So the arithmetic intensity is kind of a byte per flop. So this is generally kind of a memory-bound algorithm. The other issue with it is that if we start out with kind of naively putting particles into the spatial domain, then we get memory locality for free just by inserting the particles per cell. And so they start out contiguously. And then as we advance them, the cells or the particles can move into new cells. So what happens is that things that were accessed contiguously start to become interleaved. And this is actually a consequence for the field update, because for the particles in a given cell, they require the access to the same field interpolants. So as the particles get interleaved in this, now I have particles that I'm updating that are, and I go through the particle array in this order, but then they access data that are no longer spatially local. So the solution for that, and this is a common practice in this kind of method, is that every so often you resort the particle data so that you get back this kind of spatial locality. So that's three things that I talked about in the algorithm: the particle advance, the field advance, and then the sorting algorithm. So those are three basic things that go in. So what we did for Roadrunner, I hope people are kind of familiar with the cell processor. It has a power processing element, which is a general purpose CPU, and then it has these SPEs, which were, they're not exactly like a GPU core, but it's a statically scheduled core that's an accelerator part. So it's, logically it's kind of equivalent. So we did a lot of optimization for data structures to try and minimize data motion and be able to kind of do bulk processing for the SPEs. And initially, we only moved the particle advance onto the SPEs. There's an SPU ISA, which is a SIMD short vector language, And so we had optimized this to use those instructions. We did loop unrolling, and we used a software cache for the field interpolants. And so that worked pretty well, with the caveat that once the data kind of became spatially not close together, performance suffered quite a bit. And then initially we had the field advance, and sorting algorithms were left on the PPE. And so another thing is that this code was already kind of highly optimized for standard, CISC like Intel and AMD processors. So I really like this slide. This is from Kevin Bowers. He calls it Amdahl's whack-a-mole. And so this is kind of, when we started out with VPIC, 96% of the computation was the particle advance. And this is a single precision code, and the original code uses SSE intrinsics, so it gets very good performance. And basically everything else was kind of 4%. So if we just apply Amdahl's law to that, then we would expect something like this. We actually had a measured speed up if we look at just the acceleration for the SPEs of about 16x speed up. And so if we stick this into Amdahl's law, then we think that we get 10x maybe. So Amdahl's street justice is that when we went to the cell, we got the great speed up on the particle advance, but the PPE is under provisioned, and so it slowed down significantly, and it sapped our kind of theoretical speed up that we expected to get. The reasons for this that have been explained to me is that the PPE, in order to get kind of everything to fit onto the cell processor that they wanted, they stripped out kind of a lot of the out-of-order logic instruction windows for the power processing element, but we were using a compiler that kind of wasn't able to optimize for this now essentially statically scheduled core. And so it got pretty bad performance. I guess this was the first point that I thought of making with respect to Fusion, is that when we get these Fusion processors, in order for it to be useful for us, it needs to have a general purpose processor that is reasonably provisioned, because it makes it a lot easier to do things that you would want to do with a general purpose processor. For VPIC, the solution was that we moved the sorting and the field advance to the SPEs, but that was difficult because we didn't have OpenCL. We had to do this in libSPE, which is kind of a lower level thing. It had to be vectorized, and so it wasn't kind of a trivial thing to decide, okay, I'm going to run this on this processor now, and it creates a lot of overhead. It's fine, and it's worth it if then you end up running for 4 years on this big machine and doing science, but it's not, most people can't afford to put that kind of development resource into it. So I think this is a fairly lame conclusion for this part of my talk, but that was kind of the point, is that I would like a Fusion processor that is, maybe not balanced in terms of performance, but at least doesn't give me a crappy general purpose processor. This is my mock-up just of the differences with kind of the current PCIe attached GPU accelerator and then the Fusion device. So some of the pros and cons for the GPU, and I think I'm stating pretty obvious things here. And right now we have GDDR5 on the GPU, so we have high bandwidth in some sense. Actually, one point, and this is a pet peeve that I would like to make, I guess, is that a lot of people kind of naively say that GPUs have really high memory bandwidth. And that's true in absolute terms relative to some of the CPUs that use DDR3. But the more relevant thing for my world in doing computational methods is kind of the balance of that. So if I look at a GPU, it may have 150 gigabyte per second, but the theoretical throughput of the device is huge. And so if I look at the ratio of kind of how much data can I get to the processor versus how many floating point operations can I do on it, kind of the remarkable thing about GPUs is not that they have this absolute bandwidth, it's that they took the kind of same crappy relative data motion to arithmetic throughput and we're able to scale it up. And if you kind of compute it, then you get like a DDR3 Intel processor has about a 20th of a double word per floating point operation that it can do. And that's maintained up to a GPU on these. So that's an important thing. But once we get on the device, then we do have this high, we have high memory bandwidth compared to the Fusion processor. So if we look at just the GPU part of Fusion, it's limited now to this DDR3 RAM and has lower bandwidth kind of relative. So I think that's something that I say is a con. We have lots of cores on the GPU device, and then for current implementation, it seems like there's lower invocation latency for enqueuing kernels onto that device. So the biggest con, people mentioned this, is that now I've got to make these choices about when can I afford to go across the PCIe void to compute on this device. And I guess for a lot of our codes, we actually try and just leave the data on the GPU. But if I think of if I'm on the host and I want to decide on how I'm going to allocate resources, if I want to do some kind of function offload, then I have better do a lot of floating point operations on it once it gets onto the GPU. Otherwise, it's just pointless to do it. So data motion across the PCIe bus is a big negative thing. And then, for right now, we're effectively doubling the amount of memory that we require for a simulation because we kind of, some way I have to do pre-processing tasks and communication with MPI, for instance, and that right now is going through the host processor. And so I can't avoid having some memory allocation of state data on the host. But if I want to try and leave things resident on the GPU to get performance, I have to allocate memory down there. And as our keynote speaker just said, data motion and actually just even data are energy. So I have to pay for that somehow. And because of the kind of current state of things, I have to pay that cost twice. Then just kind of logistically dealing with multiple address spaces. This is actually kind of a pro and a con. I think that having to handle multiple address spaces exposes to you more explicitly what your data motion is. And so if you're a developer and you're trying to move to heterogeneous system or GPU, just since you've got to move those data down there, you now are more aware of what you're actually doing. So I think that's a good thing, and I like the ability to kind of explicitly control data motion. But if you take kind of the average application developer, they think that sucks. They see something like that and they're, why would I want to do that? So, it's for many people that's a real disadvantage. And now my thing down here, which will be maybe we'll see was relevant, is if I look at like a total time to execute something on a device, and I guess I mean here device as being like my GPU, then I have some kind of invocation cost that I'm going to pay just to launch something on that. And then if I have to move the data down, so I've got to go from host to device to get the data to the thing, and then I have whatever the computing kind of efficiency is on that device, and then I've got to move the data back up to the host. So when I first heard about Fusion, I thought, aha, they'll take this awesome computing thing, GPU, with this kind of high relative memory bandwidth and just stick it onto this thing, so now we won't have the PCIe bus to go over anymore. And that's kind of the idea, but it's not quite true, because when you put these onto the same silicone, you now have to have kind of the same memory subsystem. I'm not an architecture expert, so I don't know what kinds of technical innovations there are going to be, but there's a real hit to that. You're not getting the same GPU in Fusion that you had as kind of an accelerator card. So That's an issue, but then the advantage is now you've got a shared address space. So in principle, you don't have to have 2 copies of your data. You also don't have to pay that cost to go across the PCIe bus now because you're just going through the memory bus. So there's a trade-off of having these devices together but having this kind of not so great memory bus right now versus having to traverse the PCIe bus but having the kind of faster relative bandwidth. So for these cons are kind of based on the evaluation product that we got. I mean, I think there will be reduced memory bandwidth for a while. I don't know how they'll overcome that. Like, I don't think that you could have 2 memory clock speeds or something on the same device. And I think one of the issues is simply the pin area that you can stick onto the memory with the DDR3. So that'll probably stay an issue. Right now we have fewer cores, so if I just compare the GPU part to on the Fusion to an ATI or NVIDIA card, then I have it's a laptop part, so of course it doesn't have that much computing power. And right now there's very high latency when we run things with OpenCL. There's a pretty high startup cost, but I think that that's a driver issue. It's not. There's no reason that that's going to stay. So if I look at my total time for the Fusion device, then I have now, kind of in theory, I have this cost of doing the invocation, and then I have some kind of performance. So these are my conjectures about what I would expect to see from from comparing a system that had a discrete GPU versus the Fusion. And we've kind of seen this before just with experiments that we've done with our multi-core CPUs versus GPU on some work. And so it looks like, this is, to me, just logical. If I'm going to move across the PCIe bus and I do big buffers that can kind of take advantage of the burst rate of the PCIe and then do something very arithmetically intensive with those data once they get down there, then the discrete GPU looks like a good option. So I guess this is not too good to see, but this is my cost to enqueue, which potentially could be higher because the enqueuing of the kernel has to go across the PCIe bus. I have hosted data, or hosted device back to host cost. Now, if these are much less in total time than the time that it takes for me to compute on that device, I'm going to win. And potentially, that time is much less than what I would have on the Fusion part. So this is the Fusion enqueue and the Fusion computation. So the conjecture there is that we can afford to use a function offload model, which is kind of the standard GPU thing. For Fusion, and this is, I think the keynote speaker made this point kind of, we have small granularity things. I can afford to go to the Fusion device much more often because I don't have to pay that data motion cost. And so down here, you can't really see very well, but if I have my invocation cost and the total time of compute for the Fusion device, if that's much less than this whole round trip thing on the GPU, then I can use this heterogeneous execution model, and I should get some better performance. And I mean, the compute speed of the discrete GPU can still be much greater than the Fusion device, because I'm doing this data motion. So Fusion doesn't have to be as beefy as an ATI or NVIDIA card for it to pay off. This is in motivation kind of for the performance test that we did do. So our Fusion hardware, looked up, it's I forget what the name of what's the code name? Well, it's okay. So we had Bobcat Brazos, and what is it? Sakat, right? That's what I was looking for. This is just the laptop part that NVIDIA gave us. The things, I guess we don't really have to know anything here. I have a picture of what they sent us. So this is our Fusion system. I'm not sure if someone showed a picture. It's got a laptop hard drive, and then that's the actual Fusion APU, and then we have some memory DIMMs. And NVIDIA was nice enough to give us a stand to put it on. We have a lot of hardware, so we just realized that it was sitting on that when I took the picture. I thought it was funny. So put it to good use. So I'll explain more about the performance test that we did. We had our Fusion, and the thing to notice here is that this does have an 18-watt TDP and then kind of 80 gigaflop theoretical single precision. We have, in a newish cluster, we have FirePro 7800 cards. So, I mean, you can read the stuff. It has fairly good memory bandwidth, but then at the cost of some more power. And then the Tesla, I was actually very surprised. I didn't realize that the TDP for the 2050s was that much more than the ATI card. So I'm going to show timings for some benchmark tests. So that should alert you to be very suspicious about what I'm going to say, because this is kind of a synthetic test. We haven't done optimizations, and so I really only kind of mean for people to interpret these as characteristics of behavior and not raw kind of absolute stuff. So let me tell you what exactly we did. We wanted to try to see if our idea that if we're working on fine-grained data buffers with Fusion would perform better than having to pay the overhead of going down to the GPU, and then as these buffers get larger, we would kind of see them flip-flop, and we would get better performance with the GPU. And we've observed this on actual codes before, so it's not a real stretch. So our test was we just allocated some data in, logically in the host memory, and then we would compute a random offset. We did this to kind of try and keep it from. We wanted to see what happened if we didn't do what we normally do, which is to byte align everything to cache line alignment and do all of this kind of careful things in sizing data. You'll see some impacts of that. So we're just kind of randomly jumping out there. We get a buffer that is of some size that we want to try and compute. We write that down to the device, and notice that for the Fusion system, for Windows only, there is the AMD APP SDK, and that is, I guess it's a newish version of OpenCL support that allows a zero copy for memory. So that I can, the only difference between the implementation of this, we did it in OpenCL, is that for the Fusion part, we pin the memory with a map and a host pointer allocation on the outside, and then we run our thing, and then we unmap it. So I forget what the actual code thing is, but I think this is what this SDK allows you to do, is pin that memory, and then it doesn't have to copy it back and forth to the device. But then on the GPU, we tried doing mapping and then also an explicit read and write buffer to move the data back and forth. Then we execute an OpenCL kernel. Our kernel, I guess you can't really see, it's really simple. It's not optimized, so it's for vector operations, but it's a MAD, basically. So it should, it's just incrementing something. We keep the compiler from kind of optimizing it out by passing in the count and multipliers for this. So it actually does run something. So we execute that kernel, and then we read the updated buffer or force the unmap. Okay, so I think this next slide is going to be some results. So we will investigate the mysteries of Fusion. So the red is the explicit map or explicit read and write buffer for the 7800, and then the black is the Fusion. One thing to notice, so AMD has a problem here, and you'll see in a slide with their driver, I think, because the mapping here, if we just try and use the map for the GPU, it really just fails. It gets terrible performance. If we think about kind of the TDP of the Fusion and just the throughput capabilities of it, it's actually doing okay. I mean, we have kind of the weird stratification of the results has to do with a preference for particular buffer sizes. And so it's probably partly due to alignment, and it seems like it likes particular numbers. We saw this with some demo code that we did for supercomputing a couple of years with OpenCL, and this is something that's consistent across all of the architecture. So you see the same kind of stratification with NVIDIA cards also. So this is where the talk, in my mind, falls apart, because this is not, it's not a nice graph where for these small buffer sizes, I'm getting better performance on Fusion, and then as I go out, I get better performance on the GPU. And I think that we just did this like last week. I wanted something to talk about that was actually Fusion. And so I think that we need to go back and do some OpenCL profiling to actually time how long it's taking for the thing to execute the kernel, which we can do, so we could normalize these results. But if you just look at them individually, so there are some places where the Fusion guy actually does beat it, but it looks like it's just an artifact of this preference for certain buffer sizes. So, when we're running actual simulation codes, we usually look at what the users requested, and then we pad it out to something that we know is going to get good performance and use that buffer size. The other really weird thing to us, and this concerns Marcus kind of more than me, but if you look out here, this drop off here and here is that I have a number of work items where there's actual hardware that I can subscribe. Once I get bigger than that, that's where that fall off comes, and we would expect it to be linear. Benedict Gasser told me that maybe it's just overhead or something, but Marcus is convinced that this really should be a straight line instead of kind of this parabolic fall off. So that concerns us. But we also see this, yes? The bottom is a log scale, and so it's a semi-log plot. Is that true? Yes. Maybe that's my problem. Okay. Actually, I do have a log. Well, let me keep going. This could be flawed for sure. That's kind of I apologize for it. So this next thing is disturbing if you're an AMD advocate, but it really shouldn't be, because I think that it's probably has more to do with the fact that we didn't vectorize this. So this is looking at now NVIDIA, a Tesla, and it's a C2050. So it's getting kind of better relative performance. That's not so worrying because we haven't vectorized the ATI stuff, and maybe it really needs the short vector intrinsics. The other thing to consider is that the TDP for the Tesla is much higher than the ATI. So if we were to look at kind of what does this cost me in energy to use this thing, that would balance out some. The thing that's more disturbing is that when we use this lazy, just kind of map and unmap thing on the Tesla, it's getting very good performance. And so my question to AMD is, why are they down here with their OpenCL driver on this map when with the identical code in OpenCL, I'm up here with the Tesla? So the next thing that we put in here was to look at just some normal CPUs, and that's interesting. So they're performing quite well. This is an Opteron 6168, so it's we had 4 sockets of 12 core, and right now OpenCL doesn't have support for fissioning devices. So when we enqueue the kernel, it's running on all of those things as kind of one logical device, and so it gets pretty interesting performance. It It also kind of drops off. I don't have a great explanation for that. And then this is a log-log plot, so now I get these straight lines, which is, I think, is still a quadratic drop-off in performance. Okay, so conclusions. I mean, I don't have any great conclusions. I think that this bears more investigation. We're supposed to get 2 of the LANOS systems coming this week, and so it's unfair to look at a low energy laptop part and compare it to something that's a server class GPU. And I think that we definitely need to do much kind of more careful analysis to understand what's happening with performance. Some general things, I don't know, I'm disappointed in my own talk, but if I can just make some statements, I mean, I really think that heterogeneous computing is the way to go. It's clear that there are advantages of it. One picture that I didn't put up is, at least for the time being, an interesting option would be that you have a fusion device and then maybe you have a discrete GPU still. So you have some more choices. I mean, you can go CPU if you need some kind of really general conditional thing, and then you have the fusion GPU cores that you can go off to, and then if you've got something that's a big enough job, you can go off to the GPU and do it there. My other work that I do is concerned primarily with trying to add and exploit and increase the amount of task concurrency that we can do with these things. I should have put up a slide, but I have this idea that we could have really kind of a hybrid node that's got fusion parts and GPUs and FPGAs, and then OpenCL is kind of the glue that allows you to program all of that and exploit it. And so, yeah, I think OpenCL, actually, I just got back from the meeting, and that's, I guess I'm not sure if I can say this, actually. One of the areas where OpenCL could improve is in exposing kind of a richer task parallel programming environment, because right now it has very nice data parallel things. It needs some task. I think many people agree with that, so I will stop there. Thank you.